Welcome. We're going to look into the probability primer, which is the 3A appendix. Probability basics. The theory of probability deals with ideal theoretical mathematical models. It does not really deal with physical objects. That's the first thing to remember. But these theoretical mathematical models can be useful. One of the things that is often forgotten to be mentioned is that these are probabilities over the long run. And so you need to look at the long run data to average out fluctuations. Let's look at the probability of picking a single item. You first need to define the population of objects. It's called the sample size. And the probability of picking a single item is 1, because it's one item, divided by the sample size, and the sample size includes that item. So if I have a bag of balls numbered 1 through 10, the probability of picking the 1 is the number of balls that has the 1, which is 1 ball, divided by the total number of balls, which is 10, so it'd be 1/10. If I have a collection of 10 numbered balls, numbered 1 through 10, what's the probability of picking the ball with a 1 on it? It's 1 ball divided by 10. Now the interpretation is you have 1 in 10 chances of picking the 1. On average, a 1 will be picked every 10 tries. To wind up at that 10% probability, you may need to do the experiment thousands of times. What about picking a sequence? You use something called the probability multiplication rule. The examples we have here are a simplified application of this. I'm not going to go into more complex applications. The probability multiplication rule is you break the problem into a sequence of steps, you estimate the probability of each step, and then you multiply the probabilities together. This is most useful when the steps have the same probability and are independent of each other, which is what we're going to talk about here. For an example, if I have a collection of 10 balls numbered 1 through 10, what is the probability of picking the 1, putting it back, and then picking the 2 ball? Is it 2 divided by 10? No. Is it 1 divided by 20? No. Based on what we just heard, it would be the probability of picking 1 ball times the probability of picking a ball, which is 1 over 10 times 1 over 10, which is 1 over 100. The interpretation of this is you have a 1 in 100 chance of picking the 1 and then the 2. Alternatively, on average, this sequence will occur every 100 tries. Can chance count to 10? Here's an example. We have a collection of 10 numbered balls, 1 through 10. What is the probability of picking the sequence 1 through 10, putting the ball back each time? So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, there are 10 possible independent steps. Each step has a 1 over 10 probability. That's 1 is picking the right ball divided by all the balls, and there's 10 balls. So the total probability is 1 over 10 multiplied by 1 over 10, and do that 10 times, which is 1 over 10 billion chance of this happening. That's pretty small probability. Chance requires 10 billion tries to count from 1 to 10. If you were to draw a ball every 5 seconds, it would take over 1,000 years to arrive at that sequence. Here's just a side comment, is that limited intelligence can easily do this in the first try. Limited intelligence is much more efficient than probability. A 5-year-old can do this in seconds. It can order the balls from 1 through 10, picking them right each time. So chance is extremely inefficient compared with intelligence, and this is a root premise of the intelligent design movement.